Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. We stopped at using delta P for generating flow and for whatever Mach number. We just talked about the basic supersonic tunnel, and if it is a subsonic tunnel, the only difference will be that it need not be a convergent divergent nozzle, it can just be a convergent nozzle. That is the main difference. Now from there we want to go to other intermittent facilities which may also be used for studying flow around bodies for high Mach numbers. Okay. Till now we considered all the flow facilities, they are all related to tanks storing pressure energy of the gas, either it is negative pressure or positive pressure, it is storing some energy in the gas and that is used for creating the flow. Now this time there is something else which is going to give the energy to the flow. That does not mean there is no pressure involved, there is still pressure involved, there is still going to be, finally the pressure is the one which is going to create the shock, okay, and that shock, starting shock has to go through your tunnel for you to get the supersonic flow behind it. That is supposed to happen, but the way we create it will be slightly different. We will look at the other variants today. Okay. The first thing I want to do is mechanical piston drive. Okay. This is going back to the basic way of creating a shock which we discussed when we talked about I have a tube and I have a piston and the piston is moving this way. If it moves into the flow, this is going to create a shock. That is a basic idea. I am going to I believe I showed you animation also on this long back. We just push this and that is going to create a shock going through, and behind that there will be a flow which could be subsonic, supersonic depending on the Mach number of the shock or depending on the piston velocity. If the piston is going supersonic, you will get supersonic. Okay. This is one way of looking at the problem. Okay. But this is not going to help create a flow facility. So it is going to be the flow facility which I am going to talk about is a piston driven facility, but it still has a high pressure tank. Again it looks like a high pressure low pressure ordinary wind tunnel. The main difference comes here when I put a piston inside here. I put a thin disc in a tube, circular cross section, and I am going to have a diaphragm here. This is a diaphragm and there is a second diaphragm here. Okay, these two are diaphragms. Okay. Now let us think about what will happen if I break the first diaphragm. Let us label it 1 and 2. If I break the first diaphragm, what is supposed to happen? It is going to feel the pressure difference across here. I am assuming that the pressure in here is something in between the high pressure and the low pressure in the tanks. Okay, it is something in the middle, and when I break the diaphragm 1, somehow it is like a balloon and I break it and there is no more of that material sitting there. If I imagine something like that, suddenly this lower pressure gas is experiencing a higher pressure gas. It is a local shock tube. If I think about it, this is a very short length shock tube. What will happen? There will be a shock created and that is going to go to the end, and now I am going to say the end wall is not actually a fixed wall, but it is a piston. The shock will go bounce on it and come back, right, like any other thing. immediately after it bounces back, what is going to happen? The pressure behind the reflected shock is so high on one side of the piston, other side is still the same original low pressure. What is going to happen because of that? The piston experiences a net force this way, the delta P times the area of the piston, that much force is being experienced, and if I make sure that the friction between the piston and the tube is very, very small, that is I am calling it the free piston. If I have a free piston, then it is just going to be accelerated very fast, okay, accelerated very fast because there is very little drag, there is only force acting and there is nothing to resist it. So, there will be a good acceleration. If I think about mass being very small for this piston, all the force is now converted to mostly acceleration, mostly velocity, kinetic energy. If I think about it that way, it is a lightweight piston with almost zero friction. It can never happen that there is zero friction. Okay. So, there will be some friction, but the friction is really small and it is very lightweight piston. If I have such a system, then the piston is going to move extremely fast, right. I used this pressure difference to create a high pressure locally here, and then that piston moves very fast, and because of that piston moving fast, now I am going to create another shock that is going to go this way. Is this shock going to be stronger or was the original shock stronger? First one, let us say diaphragm 1 breaking, that will create a shock, and that reflected and it came back and the lightweight piston is travelling with some velocity and that is creating a shock. Which one will be stronger is the question. What gives the energy to the second one? What gives energy to the second one? This piston movement. What gives energy to the piston movement? The first one. Which one will have more energy? The first one. In theory, it will be the first shock that will create more. Then why do we use this? I just remove this and that shock can go and hit this. Then that becomes your reflected shock tunnel that you already know. That is one design we already have talked about. Okay. If I have a piston, there is something special that will happen now. That is why the piston is there. Okay. Now, this shock develops, and when it reflects back, when this wall starts moving, there will be expansion fan going that way and killing that compression reflection back. Okay. So, eventually this piston will start getting force from this side also. This high pressure will start pushing the piston also, but it got an initial momentum this way and it is moving in. While this is moving in, what is happening on this side? There was a shock created. Now, I will say this diaphragm is a little stronger and it can hold a little more pressure difference across. What will happen? It will go bounce, come back. When it is coming this side, the flow on here is zero velocity, but the piston goes and attacks that shock now, right. So, now the reflected shock will be even stronger than a straight sitting wall and the shock comes and reflects on it, right. So, what is going to happen? I am accelerating the shock even faster, the reflected shock is going to go even faster, and if I wait for it some 2-3 iterations of this reflection, I can create really high pressures here. Okay. But think about it, how much test time do I have? Only this much. Why do I say that? The piston will be moving in after some time and that is the actual compressed this gas that I have. Okay. And I finally break this diaphragm. Basically, if the pressure reaches such a high value that the pressure difference cannot be withstood by your diaphragm, it breaks and immediately the flow is expanded through this nozzle to get to whatever Mach number and temperature and pressure we want. That is the overall idea. Now, I am going to say one more special thing about this. Now, I can choose my test gas to be anything and I do not need to fill the whole chamber of high pressure with that. Okay. Now, I need to fill only this chamber with it, that test gas. Let us say I want to have a crazy test gas of xenon with iodine or something like that, some crazy, I do not know why I chose that combination, something, I just chose something, fluorine and xenon, I guess, something like that. I choose some crazy gases inside. That will be very expensive to fill this big high pressure chamber with it. Okay. Fluorine is a very reactive gas, typically it is much more difficult to store fluorine. We do not want to do that in high pressure even. Okay. Instead, I can fill only this region. This is nominally average pressure probably close to atmospheric pressure. Storing that is easier and I don't need to have huge volumes of gas. This is easier. That's one good thing about this tunnel. I can use special gases. If it is just air, I don't need all this. I'll just use a shock tube, and shock reflected tunnel is better than this probably. Okay. Now I'll think about what should be the size of this piston. Typically people use something like 2 to 3 inches. I have one information from one of the tunnels. It is having a 40 mm dia and the piston weighs only 15 grams. Lightweight disc, but the disc should be such that it does not topple and fall down like your carom coins, right? We do not want that to happen. It should still be sitting there. It should be thick enough that it does not go topple and fall straight. I cannot make it a very thin disc. It has to be having some thickness but still lightweight. Okay. They can of course use low density materials, not very difficult to do. Okay. Since I am reflecting this several times across here, shock is reflected 2-3 times, I can create very high. It's no more P5 and T5 as in a reflected shock tunnel. It's probably like T8 or T10 or whatever, some very high number. It's going to reflect each time. We will have to keep numbering them. Eventually it may become T5 will become T7, 7 will become 9, 9 will become 11, something like that. Maybe T11 and P11 can be very high, and I will get a very high P0 and T0. In case I want to do experiments with very high P0 and T0, I am going to use this, and then that will rupture this, and I am going to start with that and go to this condition. Reflected shock tunnel, it is not that capable of doing this, because if I am reflecting just once, the pressure jump and temperature jump may not be very high. That is one better thing about this tunnel. And the second thing is I can use some special gas and I do not need to store it for really high values, high volumes of this. Okay. And if you think about after the diaphragm breaks, it is exactly same operation as your reflected shock tunnel, nothing new. Okay. This particular tunnel is called a gun tunnel or free piston tunnel, or I believe based on somebody who first thought about it, Stoker tunnel. Different names. I believe currently people use only free piston tunnel as the name for it. Okay. These are various names given to it. Okay. Now we will go for something slightly different from this. I can think about the same free piston facility, but high pressure being created by a combustible mixture which is ignited suddenly, right? It is constant volume combustion. There is a tank which has high pressure, high temperature gas which is combustible, and I am going to ignite it. So it is a fixed volume tank, so the combustion will be constant volume process. If I add heat in constant volume, it is going to create even higher pressure than at constant, even higher temperature, and also pressure will increase, that situation, and eventually I will go to high pressure high temperature gas, and that can rupture the diaphragm and that can start the whole facility. Now I am talking about another mechanism which creates the shock. Okay. First, initially last class we discussed only pressure difference causing the flow. Now we said a piston moving can cause the pressure difference. Now I am saying combustion can cause the pressure difference. I do not need to have a piston if I think about it. I can just have, let us draw that picture again, combustion driven reflected shock tunnel. If I have a facility like this and I have my model sitting here, if I have such a facility, of course here it should be in a vacuum tank. If I have such a facility and I am going to say combustible mixture, this is your high pressure chamber, this is your low pressure chamber, like regular shock tube, first diaphragm, second diaphragm. Okay. This is a simplified version of a reflected shock tunnel if you think about it, except for my high pressure gas is now a combustible mixture which is already at higher pressure and temperature, and I ignite it. When I ignite it, suddenly the pressure becomes even higher and it ruptures the diaphragm because of that, and then that causes a shock that goes and reflects back. Remaining operation is same as your reflected shock tunnel. This is one way of doing it. The other way of doing it, of course, is putting this driving mechanism with a free piston tunnel. Then I go back to this picture and I will say here I will put combustible mixture, that will create a higher pressure and temperature, that will rupture the diaphragm one, and then it is going to operate like a free piston tunnel. That is also a possibility. Then it will become combustion driven free piston tunnel, while this problem is combustion driven reflected shock tunnel. Okay. We have in our GD lab at IITM combustion driven reflected shock tunnel, which I already told you can also be modified to become shock expansion tunnel. That is just something to do with this nozzle alone, that is easy to do. Now if I think about what are the advantages of this, I can go for higher P naught and T naught with this for the same pressurization of the gases, because locally I can create even higher pressure than what I can get from tanks. If I get combustible mixtures in tanks, that will probably be 200 bar or whatever. Now this can be even higher if I want to create. Okay. That is an advantage here. Okay. But it is a little more complex. Now I have to think about, when I want to start this tunnel, I have to think about, have I created the correct mixture, is it really combustible, is it at the correct pressure so that the diaphragm will break, will the diaphragm break before the ignition happens. All that details I have to now think about. It should not break before the ignition happens, but it has to break after the ignition happens. So the diaphragm should be calibrated better, okay, like that. There are more complexities, and it is actually a bomb. Think about it. It is actually combustible mixture sitting inside a tank, and I am igniting it. If something goes wrong, it is a safety hazard. I am actually creating a bomb inside, except for it is a controlled bomb so that it explodes only through this direction, creating a shock that side. That is the way to look at it. Okay. So it of course has some drawbacks, but it can create higher enthalpy flows. It is called a high enthalpy facility also. Okay. Now of course we go back to even earlier stages where there is much more basic way of creating flow around a body at very high speeds. What do? We just make the body travel very high speeds into stagnant gas. That is the best way to do it. How will I create a body, or how will I make a body go at very high speeds? Shoot it. Okay. So what I am going to do is, the next facility is called a ballistic range. Ballistics is related to bullets, guns, whatever, they are all ballistics. Okay. We are doing ballistics basically. What they are going to do is practically have a chamber and then have a cup like receptacle which is soft material. Okay. This is called the catcher. Okay. And in here you are going to have a cannon or a gun or something with the projectile which I want. Okay. I will have some model typically. Say I want to have a missile 4 body which is supposed to be traveling at Mach 4 or something, and I want to test it. I will make a bullet of that shape exactly, and I will have some explosives behind it, or not even explosives, just have a high pressure gas behind it and have a diaphragm which ruptures. What will happen? Locally there will be a shock created, and instead of a free piston, it is going to be the bullet that is going to fly. Now the bullet is accelerated crazily, and that is going to fly through this region. When it comes to this particular region, now I will start taking measurements inside here. typically if I want to think about flow visualization, I will start looking at flow visualization in this region. I will take photograph when the bullet comes in here, okay, like that. If I do that, then I am going to get, when the bullet is here, I may get a shock around it like this, okay, and that is our study. I wanted to see what the shock pattern looks like on this body, then I will look at something like this. This is how it is going to look. If the missile forebody looks more like our Agni missile, then it will start having a lot of steps on it, then it will have different patterns on it, and I want to study that. That can be done with this miniature forebody model with the explosives behind it, shoot it at the correct Mach number, then you get to this. Okay. What are the things I need to worry about? It should not go and hit anywhere else other than go into the catcher, which is probably a foam or some thermocol kind of soft material. You will just take it, and then you go cut it and take the piece from inside. The next thing I need to worry about is the explosive charge just right enough to get the correct Mach number at this point, and is the gas in this area stagnant all the time, or at least during my experiment is the gas stagnant. Only if the gas is stagnant, then I will get the correct Mach number based on flow velocity. Those are things I need to think about, and also I have to think about, am I setting the pressure and temperature at this section, the test section, correctly to whatever we want. That is one more thing we need to think about. Okay. The problem with our regular supersonic tunnels is, when we work with our kind of P0 and T0, when we go to say Mach 3, the pressures in the test section are not regular atmospheric pressure conditions, they are lower. They are probably like 0.1, 0.3, 0.5 kind of bar values, 0.5 atmospheres, 0.2 atmospheres, that kind of pressures. Okay. But in these facilities, I can maintain it to be atmospheric pressure, already existing air around in here, and just shoot this bullet. As long as the flow is very stagnant in here, my experiment will be clean. Other problems could be, there was one small burr or dust sitting on the turret here, because of that the bullet is not going to go straight, but it is going to have a wobbling. It may have errors like that. Okay. This was very popular long back. If you go and see some old papers where they are doing the study, they will be doing it with ballistic experiments. Okay, where they will, if you go and look at some old Schlieren photographs, okay, they would have done Schlieren around a bullet, and you see that the experiment was done exactly this method, okay, ballistic range experiments, they would have done that. Okay. The good thing about here is there is no support for the model, okay, which means there is nothing else which is going to obstruct the flow. In the other cases, I have to hold the model somehow. Say for example, if I pick this one, this is going to be sitting here, and it may obstruct my flow after some time. That is, the shock goes through and then it is going to reflect back, and maybe it is going to have some effect here. There is no such thing in this particular flow, and I can calculate the exact drag on this body directly by keeping track of how fast is it traveling through this point. If I have a set of points like this, and I just mark on this and take a video of this, it will travel very fast here. As it goes, because of drag, its velocity is going to decrease. That directly tells me the velocity as a function of time, which tells me deceleration, which gives me the drag immediately. That is one more information I can get out of this directly. While in the other case, I have to put lot of pressure transducers on it to get my pressure loading. Okay. And even if I do the pressure loading based drag, I am missing viscous effects. Here this is absolute, this is the truth. Directly it is going to give me viscous effects at that pressure and temperature. If the Mach number is also correct, then you are getting good information. But the problem with this will be, am I going to get the drag at the correct timing so that I will get the drag at that particular instant. Okay. Though of course you can do some analytical work to get to the point where I need so much energy in this explosive so that I will get to that point. Can be done, not very difficult. People have worked on this already. Okay. But if I think about, say I want to measure pressure somewhere inside, there is no way of measuring pressure on this body currently. Of course, nowadays we have modern instruments, people go back and do this now, radiometry is there. So what I have to do is go put a sensor with battery and etc. inside, it is going to send information through electromagnetic waves out like your radio waves, you are going to send it out and you can collect it. That is the next thing People are again using this nowadays because it's now having a new use for it. Okay. People can use it this way also. Okay. But if I want to think about repeating the experiment can never be repeated. Okay. I cannot do the same thing again and again. The next time when I shoot the bullet, even if it is the same bullet and it is not damaged by the catcher, if the shape does not change at all, even then when I put it back and fire it, the next time maybe the explosive is not exploding the exact same pressure, maybe slightly lesser, slightly more, whatever. So I may have some variation. If I was expecting some particular drag at this point, now the same drag may happen a little earlier or a little later. Okay. It is not going to be exact repeatability. Okay, but you can work around it. If you know what is going to happen, you can think about it, but you have to now think about it. In the other experiments, model is fixed. So when I say I repeat, if I check the pressures are same, Mach number is the same, and I can repeat the whole thing. That's easier for us. That's a little difficult in this particular facility. Now there is one more special facility. Okay. Till now we talked about energy for the flows given by stored pressure, moving piston, combustion. Okay. And this explosion ballistic range is also either stored pressure or combustion, one of these two. Okay. Now we will give one more, electrical heating. Okay. It is not simple electrical heating, it is arc heating. Arc heating. So it is actually called a plasma arc tunnel. Plasma arc tunnel. Previous thing is called ballistic range. Okay. So it looks like this. Actually, throat should be correct. Some CD knows it, and I will have my model. Setting somewhere like this. Okay. Now I will draw the remaining portion of this. Okay. Do not finish this, I will come back and draw something, but I will just tell you the principle basically. I am going to have say an axisymmetric body here, and it is going to be considered as a positive electrode. It is not completely blocked positive electrode, it is going to have a straight hole through the center. This is positive electrode, this is negative electrode, and now I am going to say the negative electrode is shielded on the sides with some insulated material, so that only the front portion is going to send the electric field. If that is the case, electric field will typically go like this. Actually I am drawing the arrows the other way, arrows go from positive to negative typically. Something like this. So what I am doing is I am concentrating all the electric field lines here. It is going to create a lot of electric field strength, which immediately breaks down the gas to ions and electrons, and that immediately is going to cause lot of energy dumping into the gas. Why? I have ionized the gases, which means I gave some energy into the gas to knock off the electron from the molecules of the gas. Okay. That is one way of dumping energy. Other way of dumping energy is those ions are now going to be moving. Okay. Electrons, ions, neutral molecules, everything is going to be moving because of high temperature. Okay. And now I am going to say they predominantly are going to go this way. Okay. Now if I say actually I am not allowing it to go out anywhere, this is going to be closed on this side, so it is going to go only this side. Now I will say it is a settling chamber here. settling chamber here, and this is my nozzle, and after the nozzle I immediately have a model, and this is my low pressure tank. I have this particular system. Let's think about something like this. Simple enough supersonic facility. I am not having a diffuser in this case. Okay, I have something like this. This is my flow facility. Now I have to think about one special thing. Because of this arc heating, this electrode gets too hot. So now I need to have cooling tubes through this. Now I am going to have some coolant in and coolant out. I do not want to say the coolant is water really, it need not be water. In fact, most likely it is not water because of high voltage. Okay. Some coolant in, some coolant out. Okay. And that is going to be cooling this whole block. Of course, I should put the same coolant on this side. I am just going to put hatch instead. You know that there is coolant for the whole block and it is an axisymmetric block. This is going to be your facility. What I am doing is essentially creating some kind of high pressure, high temperature zone locally, and that is going to be your source overall. That is going to go to the settling chamber, become a little more uniform flow, and then it is going to go through this throat and get out through this direction. If I have dumped enough energy into this region and created very high pressures and temperatures, then this can be used as a source for my flow field, and I should set my low pressure really low enough that my PB by P naught for my nozzle works in favor of creating a supersonic flow in here. Okay. So I have to set my pressures appropriately to get the required flow. Okay. Typically in this I can create T naughts of the order of 12,000 Kelvin, quite high. Okay. The drawback will be it is not going to be a neutral gas that is going to come out, it may have some ions and electrons in it, which means my gamma value will not be simple. Now gamma value will be changing. If there are molecules that are becoming ions, then I am going to have gammas that are gamma getting lower. Okay, gamma will get lower, which means I am getting more compressible. I am going to have a more compressible gas plasma sitting inside. Okay, that will start happening. And how much is the operation time for this? It again comes down to very low. Right? Why is it very low? I have to dump so much electrical energy from somewhere. It was stored in say a huge capacitor somewhere, and only till the capacitor gets discharged I can do this job. And then again I have to wait for charging the capacitor, and then again fire it once. That is all I can do with this facility. Okay? So the time of running depends on the size of the capacitor and the size of the wires I am using, etc. Okay, since it is a high current setup. Typically people use argon with this. Okay, argon is a noble gas which is easily ionizable, okay, and it is reasonably available in our atmosphere. Okay. So people use it's very easily ionizable noble gas, simple enough to work with. Okay, but 1.66 gamma is no more 1.66 for this, it is going to be lesser than that. Okay, I cannot tell the value, it depends a lot on what is the exact current going through and how much is the ionization efficiency, etc. But gamma will not be 1.66, it will be slightly less than that. Okay. And one more thing, I am jumping myself out of this course content currently. If I say that there is plasma, high pressure, high temperature plasma that is coming through this nozzle, once it goes to supersonic flow, the pressure and temperature becomes lesser. At those conditions, the plasma cannot exist as plasma and it has to recombine to form neutral molecules, neutral atoms in this case if it is argon. Okay. If that is the case, then because of this recombination, the gamma of the gas will change, the molecular weight of the gas will change, average molecular weight of the gas will change. Okay. Because of all this, I will have variation in A along this direction, variation in gamma along this direction. So my flow is a little more complex now. This enters the regime of high temperature gas dynamics. Now I have to know a little more than whatever we talked about in our simple gas dynamics course. We need to talk more about high temperature gas dynamics. Why? And my temperatures are pretty high. I need to think about this. Of course, when I go to Mach 4, the temperature is going to be much lower. It's not going to be 12,000, it probably is going to be 2,000 or so, where I cannot have ions sitting by itself. Okay, it will become recombined to neutral atoms. Okay. And one more drawback of these arc heating mechanisms is basically the electrodes will get eroded with time, because there are electrons going and bombarding into the positive electrode, and ions coming and bombarding into the negative electrode. Because of this whole thing, I am going to have erosion of, or sputtering they call it, sputtering of the electrodes will start happening, okay, which is all bad for the electrode. Eventually I have to change the electrodes. The whole setup will become a waste within so many runs. I do not know how many it is, depends on the electrodes. Okay. And now we will think about something much more. If I want to make something fly at really high Mach numbers, what else can I do? I can put it in front of a rocket, and fire it. That is one more way of making this kind of experiments. But if I think about that, I cannot do flow visualization on that. I cannot be carrying my cameras along with the rocket. Okay. To some extent I can, but I cannot do really perpendicular to the flow kind of direction. Okay. Rocket powered, you can think about. I have not seen much of experiments where they do like this, but we hear a lot about people testing out engines using rocket powered systems. Ramjets and scramjets, when they first tested, what they did was they put a rocket behind it and they fired it up so that it reaches good enough Mach numbers, and after that the engine starts working. At that point the rocket falls off. They have done something like this. Okay. So I can tell that I can just connect a rocket behind it, and that itself will start becoming useful for you. I am accelerating really high power. What am I using here? Chemical power, chemical energy. Okay. It is propellants burning, creating thrust, and that is causing the whole model to be going very high. Drawback of this, it has to withstand the launching G values. Okay, the model should withstand the G values. Initially, of course, you should anyway design for, if it is high Mach number, you have to design for the flow forces. More than that, now I have to think about G values. Okay. That is one more thing I have to think about, accelerating with a rocket. Okay. Of course, you should know it is extremely expensive. It is not simple. Typically, only big rocket launching agencies like NASA, or in fact ISRO is also planning on something like this, I believe. So some such things, only those kind of people can do this. Cannot be an institution like IITs or anything that cannot do this. It is much bigger scale than this. And you have to also think about safety of people below. It cannot be that the rocket that detaches from there comes and falls on somebody's head. So you have to think about that safety also. Typically it has to be flown over some safe sea area where they have already cleared out all the fishermen on other ships around there. Only that area they will fire things. That is true for any rocket launch anyway for us. Okay. So you have to think about that also. But the good thing about this experiment is it is really done in actual air in which I want to fly the engine, say the scramjet. If I want to fly the scramjet in some particular condition, I will take the rocket till it goes there and then fire it there. That is the best thing you can do. Okay. So people can work with that also. One more such an experiment possibility is re-entry problems, re-entry models. I will take something with my rocket, send it up into the orbit, like our space re-entry experiment SRE. Okay. We can make it go for 1 or 2 orbits, full circles, and then when it comes next time you deorbit and start coming in. Now I am really studying re-entry problem, because now I can put special sensors on that at different locations and actually study the heat transfer. Of course, first time I should over design, but later with the sensors I can find out exactly how much is the heat transfer and what could be the pressure distribution, what could be the temperature distribution, etc. And now I can check my whatever insulation tiles, for example. Okay. I can test those things. That is a good thing about re-entry based facilities. Okay. not much has been used in this mode anywhere in the world, because it is much more expensive than rocket launched experiments. Now I have to think about going all the way out of the space, out of Earth's atmosphere and coming back into it, much more expensive research. Okay. I haven't seen many people who are doing this. Maybe NASA has done it once or twice, India has done it once or twice, and that's it. I think maybe Europe also somebody would have done it once or twice. I don't know about Japan and Russia right now. I know Russia has a very huge continuously running supersonic facility, okay, which is really huge, where we test our scramjet engine. Okay, that is also there. So some such things are present somewhere. Anyways, so the next thing is transonic tunnel. Okay, till now we did only supersonic tunnel. Now we will go look at transonic tunnel. There is some special considerations you need to worry about when it is transonic tunnel. Okay. So I will give you one small bit about supersonic tunnel, then I will come back to it. If I think about any supersonic tunnel, let us say this is my test section wall and I have a model like this. I will use a different model for this time. If I have a longer model like this and somehow I am holding it, let us say I am holding it somewhere. Now because of the flow, let us say I have a shock like this. What will happen to this shock now? It is going to come back reflected. Okay. Now this shock is going to interfere with our model. That could cause trouble. Okay. That is one thing you have to think about when you are designing a model for a supersonic facility. Okay. This could cause trouble now. This is not going to be there in your real flow experiments where there is no wall around it. So your model should be such that the shock that is going from the leading edge should not be reflecting back onto the model. Okay. That is one more thing you have to worry about. Of course, if you are interested only in the front portion, it will still work. Why? Flow is supersonic, things downstream will not affect upstream, assuming I am thinking only steady state problems. Okay. I keep mentioning this, steady state is very important there. Okay. So this is a bad thing about this model. If this is the case, then I have to either move the wall more and have the wall reflect the shock somewhere far downstream. That is one way of doing it. That is typically not possible. Just because I made a bigger model, I cannot go and redesign my whole tunnel. So what people do typically will be have the same tunnel but decrease the model size, okay, such that now the shock that is reflected is going to go out of it. It will not go and interact with it. Now I can go and study expansion fan, shock, whatever. I believe we discussed this problem already, flow around external flow around bodies. We have already discussed this. This is one thing we need to think about. Other thing we need to think about is, you know, typical supersonic tunnels have a nozzle and diffuser, and we said this is A1 star, this is A2 star, and we said that A2 star should be minimum some value. If not, the flow will not start, the tunnel will not start, we said. What will happen? The shock that comes here will never go past this direction. We said that. So for that condition, it is A2 star by A1 star must be greater than or equal to P01 by P02 at Mach number of test section. Okay, for that shock at that Mach number at the test section. That is what this means. Okay. So you have to think about this. Now I will think about a special case. This model is going to be actually blocking the flow, right? This flow cannot go through the model there, which means now the actual flow available area available for the model, flow area available for the flow is only between this wall and this model and between the wall and this model. If that is the case, then now I have to think about the area decrease because I introduced a model in my test section. If the net area available for the flow, if it is less than this A2 star, then that becomes your throat, second throat, even though you have one more throat downstream. This becomes your second throat, and the shock will never cross this if A2 star by A1 star is such that it is not greater than or equal to this. Okay. So your model has a limitation both in length and in total cross section area, total frontal cross section area. Okay. In both ways there is limitation on your model. One more thing, it is not just the model, it is also the holder included. Holder is also blocking the flow. Now if I have to think about, I have pressure transducers on this and there are wires going through, and the wires I have just wrapped around this, let us say, with some kind of tape. Even that total cross section matters. Okay. Typically what they do is they put this holder as a tube and take all the wires through it. May not be always possible, but most of the times they do this. Okay. All those things matter, and typically the holders are not cylindrical rods as in subsonic flows. They are not going to have a cross section of a circle like this. They will typically have some kind of fairing around it so that it looks sharp enough. Why? A blunt body is going to have a bow shock, while a sharp body with small enough angle will have a attached oblique shock, which will cause much lesser P naught loss. What matters downstream of the model is what is the net P naught that this gas has, so that now I can think about what is the mass flow rate through this throat. Okay, not just this single first shock thing. First shock thing is the basic starting condition. Okay, this is the basic starting condition. Now because of all these extra shocks present, the P naught 2 will be even lesser. If this is even lesser, think about this ratio will be even bigger. So my A2 star by A1 star should be even higher if I have more resistances to the flow. Okay. So that to minimize that, again I have to have small models, small holders, everything small. Of course now there will be a point where we will say structurally it is not stable if it is too small. If I have a very thin rod trying to hold a huge model, it is not going to happen. So there has to be some compromise somewhere. There is one more thing we need to think about. Now that we have done this, we can go back to transonic tunnel. Okay. Transonic tunnel, mainly I am thinking about a tunnel where Mach number is of the order of 1, anywhere between 0.8 or 0.9 to 1.1 or 1.15, that kind of Mach numbers. That is what is called the transonic region, where any small perturbation matters. Okay. So we will redraw the whole thing. The tunnel looks somewhat like an in-draft tunnel. I am just drawing one of the facilities possible, and in this case what I am thinking about is it is transonic, which means my model should be sitting at the throat of a nozzle, right, because at the throat of the nozzle only you get m equal to 1. So I have to put a model at the throat of the nozzle. Okay. And now you know why I talked about that other thing. If I put a model there, the area at the throat of the nozzle is only the area available for the flow around here. So the actual throat is somewhere at this location. If I think inviscid, if I think viscous, it can be even ahead of it. Okay. We said viscous effects will have boundary layer growth, and because of that there is going to be a equivalent thinking about wall can be shifted a little more inside and this wall will be shifted a little more outside. So overall area available can be shrunk even more. That can also happen in there. Okay. So I am just thinking about some particular flow facility where let us say somehow I create the pressure disturbance. Say I will put a fan and a motor. I will cause suction here in the diffuser section. I create suction and that is going to start the flow from here. P naught is atmospheric, it is in-draft tunnel. Okay. Another way of creating in-draft facility for low Mach numbers. Okay, I can just use a fan up to 0.6 or so. I think you can use in-draft just a fan, but above that I need to go for actual vacuum pumps and storing this. This particular facility, if it is a fan, can be continuous, it can be operating for a long time. That is a good thing about this facility. So I have drawn this particular case for you, and of course the model needs a support. Okay. So this is your test section region, which actually happens to be near the throat of the model itself, throat of the nozzle itself. Overall it looks like one CD nozzle. Okay. Now say I have to think about what are all the problems that can happen. First thing is of course blockage, because there is a model sitting in this region. Okay. So my mass flow rate is going to be already lesser. Okay. Or the fan has to take that extra load to keep the same pressure drop. Okay. Mass flow rate is lesser is a nicer way of looking at things. If I think about my flow having I am thinking about a Mach number 0.9, I want to do the experiment. If I think about Mach number 0.9 here, then it is going to have choking, right? Any small area change, if you go look at A by A star for Mach 0.9, it is going to be close to 1 already, and if I change the area much more, then suddenly there will be choking in the middle, okay? And now that flow cannot go through because it is choked and I am still changing area. What will happen? That flow never happens, it resets everything and then says this point is m equal to 1 and the Mach number is not 0.9 but lesser. It resets everything, decreases the mass flow rate upstream. There will be accumulation if you think about from the point of view of Rayleigh flow, Fano flow we discussed. If the choking happens earlier or I extend the length, decrease the area more, similar to extending length in Fano flow you can discuss. I am going to say if resistance is more, there will be compression waves coming, changing the flow speeds in front of it. I wanted Mach 9.9 here, but I may get only 0.85 unless I do some more things. What they do is they will put holes on the side and keep this region at slightly lower pressure than what is in the test section, so that I will bleed out some mass flow. If I bleed out some mass flow, now I can make sure that the incoming flow is 0.9 because not all the flow has to go through this, because that is having a choking condition, but this is not. I want to send out some mass flow. Okay. Now I have to think about all these extra situations. Okay. This is to take care of geometric choking. Next thing is shock reflection. Now think of a wedge, even if it is very thin, for Mach 1 or 1.05, shock is going to be like this, right? How do we know this? We have our theta beta m curve. For very low Mach numbers, beta was very close to 90, only when it is Mach 2 it was getting more inside, otherwise it was only here. Beta was almost close to 90, all the shock is almost normal shock. Now what should be my model size for this? There is a wall here, it will go and hit back and come back straight. Now my model should be inside this itself, cannot be anything bigger. Okay. That could be a problem with this facility. Okay. So to avoid this, what people do is go and put the holes there and then put compartments and connect them all to one big low pressure facility. If I connect it to something like this and have individual valves in between, they are opened amount different amounts. If I have something like this, then I can allow for air that wants to go out through this and come back out through this, something like this. It is as if the wall is not really there, the flow will go out and come back, that is what it feels like. Something like that can happen. This is called correction in the transonic facility, and we have one such facility which is self correcting transonic tunnel in our IIT GD lab. Okay. The next only thing left is low density facility. I will just spend 5 minutes on that next class, and then we will move to how to design models, etc., and go to pressure measurements and temperature measurements, etc. Any questions? See you people next class.